Picture this. You wake up tomorrow morning, look out your window, and the sky's gone purple. Not a lovely lavender sunset purple, mind you, but a proper menacing violet that makes your stomach drop. The air smells wrong, tastes metallic on your tongue. Within hours, you're gasping for breath. Within days, you're dead, along with nearly every other living thing on the planet. Sounds like proper science fiction, doesn't it? But here's the mad thing. This actually happened. About 2.4 billion years ago, Earth experienced the most catastrophic extinction event in its entire history. We call it the Great Oxidation Event, though that rather bland name doesn't quite capture the absolute carnage of it all. Some scientists prefer oxygen Holocaust or oxygen catastrophe, which gets a bit closer to the mark. You see, oxygen, that lovely stuff we breathe every second of every day, was once the deadliest poison our planet had ever known. And when it first appeared in Earth's atmosphere in significant quantities, it didn't bring life, it brought death, on a scale that makes every other extinction look like a minor hiccup.
Let me take you back to the beginning. Earth in its youth was nothing like the blue marble we know today. For starters, there was no free oxygen in the atmosphere at all. None. Zero. Zilch. Instead, the air was a rather unpleasant cocktail of methane, ammonia, and other gases that would kill you stone dead in seconds if you tried to breathe them. The sky wasn't blue. It was likely an orangey red haze, like looking at everything through rust-coloured glasses. And life? Oh, there was life, all right. Billions upon billions of microbes thrived in this oxygen-free world. They were anaerobes, creatures that not only didn't need oxygen, but were actually poisoned by it. These weren't complex organisms, mind you. No animals, no plants, nothing you could see without a microscope. Just simple, single-celled beings that had the entire planet to themselves. These early life forms were proper clever in their own way. They'd figured out how to harvest energy from all sorts of chemical reactions, breaking down sulfur compounds, converting methane, even using the faint light from deep-sea volcanic vents. They had been at it for over 1 billion years, slowly spreading across the planet, filling every niche, from the deepest ocean trenches to the surfaces of rocks baking under the dim young sun.
The oceans were teeming with them. Scientists reckon there were probably more individual microbes alive then than there are today, even counting every ant, every blade of grass, every bacterium in your gut. It was a microbial paradise, a planet-wide party that had been going on for eons. Then along came the Cyanobacteria. Innocent-looking little blighters, not much different from their cousins at first glance. But these microbes had developed a new trick. Arguably the most important innovation in the history of life. Photosynthesis. Not just any photosynthesis, mind you, but oxygenic photosynthesis, the kind that produces oxygen as a waste product. Now, other microbes had been using light for energy before this, but they used a simpler form that didn't produce oxygen. Cyanobacteria took it to the next level. They could split water molecules, good old H2O, steal the hydrogen for making food, and dump the oxygen as waste. Brilliant for them, catastrophic for everyone else.
At first, it wasn't a problem. The oxygen they produced was immediately gobbled up by chemical reactions. Iron dissolved in the oceans would rust, volcanic gases would oxidize, organic matter would decay. For perhaps 300 million years, every molecule of oxygen the cyanobacteria pumped out was neutralized before it could build up in the atmosphere. The planet had an enormous capacity to absorb oxygen. Scientists call these oxygen-absorbing reactions oxygen sinks. But here's the thing about sinks. They can fill up, and that's exactly what happened. The cyanobacteria were too successful for their own good, or rather, too successful for everyone else's good. They multiplied like mad, spreading across the sunlit surfaces of the oceans, forming massive floating mats and coastal colonies, Each one was a tiny oxygen factory, bubbling away day after day, year after year, millennium after millennium. The numbers are staggering when you think about it. A single cyanobacterium might produce only a minuscule amount of oxygen, but multiply that by trillions upon trillions of them, working away for millions of years, and you're talking about a proper atmospheric revolution. Scientists estimate that at their peak, cyanobacteria were pumping out oxygen at rates comparable to all the plants on Earth today.
The first sign of trouble came in the oceans. Iron that had been dissolved in the water for billions of years suddenly began precipitating out as rust. If you've ever seen those spectacular banded iron formations in ancient rocks, those beautiful red and black stripes, you're looking at the calling cards of the oxygen catastrophe. Each band represents a pulse of oxygen production, a wave of death sweeping through the oceans as dissolved iron grabbed onto oxygen and fell to the sea floor. For the anaerobic lifeforms, this was the beginning of the end. Oxygen was creeping into their world, and there was nowhere to hide. It seeped into the water, infiltrated their habitats, poisoned their food sources. Imagine if the air around you suddenly started filling with chlorine gas. That's what it was like for them, except they couldn't hold their breath or run away. The dying began in earnest around 2.4 billion years ago. That's when free oxygen finally began accumulating in the atmosphere itself. All the oxygen sinks were full up, every bit of exposed iron had rusted, every reactive mineral had been oxidized. There was nowhere left for the oxygen to go, except up into the air.
The methane in the atmosphere didn't stand a chance. Oxygen attacked it viciously, breaking it down into carbon dioxide and water. Now, methane was a powerful greenhouse gas, much more powerful than carbon dioxide. As the methane disappeared, Earth's planetary thermostat went haywire. Temperatures plummeted. The planet plunged into what might have been the longest, coldest ice age in its history, the Huronian glaciation. Picture this, ice sheets stretching from pole to pole, oceans frozen solid to depths of hundreds of meters, global temperatures so low that even the equator was buried under glaciers. This wasn't your garden variety ice age, this was Snowball Earth, a frozen hell that lasted for 300 million years. The purple sky I mentioned earlier, that might have been from the interaction of oxygen with methane high in the atmosphere, creating a hydrocarbon haze that would have given the sky an eerie violet tinge. For the anaerobes, it was a double whammy. Not only was oxygen poisoning them directly, but their entire planet was freezing solid. The warm, cozy world they'd known for over 1 billion years was gone, replaced by a toxic, frozen wasteland. They died in their trillions, their quadrillions, numbers so vast we don't even have proper words for them.
The statistics are sobering. Scientists estimate that 99% of all life on Earth perished during the Great Oxidation Event. Let that sink in for a moment. 99%. If we had a similar extinction today, only 80 million humans would survive out of 8 billion. Every major city would be a ghost town. Entire continents would be empty of life. But the microbes had it worse than that. Entire groups of organisms, whole branches of the tree of life that had been evolving for hundreds of millions of years, were wiped out completely. We'll never know how many unique forms of life disappeared forever during those dark centuries. The fossil record from that time is frustratingly sparse, but what we do find tells a tale of utter devastation. The survivors were forced into exile. Some retreated to the deep ocean where oxygen still couldn't reach. Others found refuge in thick sediments, in the guts of other organisms, in any pocket where the old oxygen-free conditions still prevailed. These remnant populations exist to this day, living fossils hiding in Earth's most extreme environments, testament to one of the greatest catastrophes in our planet's history.
But here's where the story takes a remarkable turn. Evolution, as they say, finds a way. Some organisms didn't just hide from oxygen, they learnt to use it. You see, oxygen is incredibly reactive, which is what makes it so dangerous. But that same reactivity also makes it a brilliant fuel for metabolism. Organisms that could harness oxygen could extract far more energy from their food than their anaerobic cousins. The first oxygen breathers were probably reluctant converts, developing just enough tolerance to survive in low oxygen environments. But over millions of years, they refined their oxygen handling machinery. They built enzymes like catalase and superoxide dismutase, molecular machines that could neutralize oxygen's toxic effects. They built elaborate respiratory chains that could harness oxygen's power safely. These early aerobic organisms had stumbled upon a metabolic goldmine. While their anaerobic cousins could extract only 2 molecules of ATP, the cellular energy currency, oxygen breathers could get 36 or 38. That's like upgrading from a push bike to a Ferrari in terms of energy efficiency.
This massive energy boost had profound consequences. For the first time, life could afford to become complex. You need tremendous amounts of energy to maintain large cells, multiple chromosomes, elaborate internal structures. The oxygen-powered metabolism made all of this possible. Without the Great Oxidation Event, we'd still be stuck with simple microbes. No animals, no plants, no fungi, just an endless soup of single-celled organisms. The cyanobacteria themselves did rather well out of the whole affair, as you might expect. Not only were they immune to their own toxic waste, but they now had much less competition. They exploded across the planet, forming vast mats in shallow seas, painting the coastlines green with their chlorophyll. Some of them even began experimenting with multicellularity, forming chains and filaments and eventually more complex structures. About 1.5 billion years ago, one of these oxygen-breathing cells pulled off one of the most audacious tricks in evolutionary history. It swallowed a cyanobacterium whole, but instead of digesting it, it kept it alive inside itself. This captive cyanobacterium became the first chloroplast, the structure that allows plants to photosynthesize. Every green plant on Earth, from tiny algae to giant redwoods, owes its existence to this ancient cellular merger. A similar event gave us mitochondria, the powerhouses of our cells. Some ancient cell swallowed an oxygen-breathing bacterium and turned it into a permanent power plant. These mitochondria are why you and I can use oxygen to power our bodies. We're literally carrying around the descendants of ancient bacteria that learned to thrive in the toxic atmosphere created by the Great Oxidation Event. The rise of complex cells with internal power plants set the stage for everything that followed. The Cambrian explosion 540 million years ago, when animal life suddenly diversified into myriad forms. The colonization of land by plants and animals. The rise of dinosaurs, mammals, birds. The evolution of consciousness, intelligence, civilization. None of it would have been possible without oxygen. It's a bit mind-bending when you think about it. The worst catastrophe in Earth's history, an extinction event that killed 99% of all life, was also the necessary precursor to complex life as we know it. Those ancient cyanobacteria, mindlessly pumping out their toxic waste, accidentally terraformed the entire planet and made our existence possible.
The Great Oxidation Event also left its mark on the planet in other ways. The oxygen atmosphere created the ozone layer, which shields us from deadly ultraviolet radiation. Before oxygen, life was confined to the depths of the ocean or beneath protective layers of rock and sediment. The ozone layer opened up the shallow seas and eventually the land itself to colonization by life. Oxygen also changed the very chemistry of the planet. It created new minerals that couldn't exist in an oxygen-free environment. Over 2,500 mineral species owe their existence to the Great Oxidation Event. The stunning diversity of gems and crystals we see today, from turquoise to malachite, simply couldn't have formed on the ancient Earth. The event even changed how the planet's geology works. Oxygen weathering of rocks on land increased the flow of nutrients to the ocean, fundamentally altering marine chemistry.
It changed the sulfur cycle, the nitrogen cycle, even the carbon cycle. The Earth after the Great Oxidation Event was a fundamentally different planet from what came before. What's particularly fascinating is how long the whole process took. This wasn't some sudden catastrophe like an asteroid impact. It played out over hundreds of millions of years, a slow-motion apocalypse that gave life time to adapt and evolve. The oxygen levels didn't shoot up all at once, but rose in fits and starts with periods of stability and even reversals.
Scientists studying ancient rocks have found evidence of whiffs of oxygen appearing and disappearing in the atmosphere hundreds of millions of years before the Great Oxidation Event proper. It seems the Cyanobacteria made several attempts at oxygenating the planet before finally succeeding. Each whiff would have caused local extinctions, preview events of the greater catastrophe to come. Even after oxygen became permanently established in the atmosphere, levels remained much lower than today for over 1 billion years. It wasn't until around 800 million years ago that oxygen levels approached modern values. This second rise in oxygen coincided with another major transition in life's history, the appearance of the first animals. The story of the Great Oxidation Event holds sobering lessons for us today. It shows how life can fundamentally alter a planet's environment, sometimes with catastrophic consequences. The cyanobacteria didn't mean to cause a mass extinction. They were just doing what life does, growing and reproducing and exploiting available resources. Sound familiar?
We humans are currently running our own atmospheric experiment, pumping carbon dioxide into the air at unprecedented rates. We're changing the climate, acidifying the oceans, triggering what many scientists call the sixth mass extinction. Like the cyanobacteria, we're not doing it maliciously, we're just living our lives, powering our civilization, feeding our children. But unlike the cyanobacteria, we can see what we're doing. We can measure the changes, predict the consequences, potentially change course. Whether we will or not remains to be seen. Perhaps some future species will look back at the Great Carbonization Event the way we look back at the Great Oxidation Event, as a catastrophe that paved the way for something new. The Great Oxidation Event also reminds us how contingent and unlikely our existence is. If those ancient cyanobacteria had never evolved oxygenic photosynthesis, Earth might still be a planet of simple microbes. If the oxygen had built up too quickly, it might have sterilized the planet entirely. If the Ice Age had been a bit more severe, life might never have recovered.
We exist because of a cosmic roll of the dice that came up just right. A bit of biochemical innovation, a planetary catastrophe survived by the slimmest of margins, a few lucky cells that learned to breathe poison. That's our heritage, our unlikely origin story. So the next time you take a deep breath, spare a thought for those trillions of ancient microbes that died so you could live. Their catastrophe was our opportunity. Their poison is our life. In the grand story of Earth, the day the sky turned purple marked not just an ending, but a beginning, the first chapter in the tale that would eventually lead to us. The Earth did eventually recover from its purple phase, of course. As oxygen levels stabilized and life adapted, the methane haze cleared and the sky took on the blue color we know today, caused by oxygen and nitrogen molecules scattering sunlight. The purple sky was gone, but its legacy lives on in every oxygen-breathing creature on the planet.
And those anaerobic microbes? They're still with us, billions of years later. They lurk in oxygen-free environments around the globe, in deep-sea vents, in waterlogged soils, in our own digestive systems. Every time you feel a bit gassy after a big meal, you're experiencing the handiwork of anaerobic bacteria in your gut, descendants of Earth's original inhabitants, still living in the style of a bygone age. In a way, we carry the entire history of life on Earth within us. Our cells remember the Great Oxidation Event in their very structure. Mitochondria to handle the oxygen, antioxidant systems to prevent damage, elaborate mechanisms to ensure oxygen goes only where it's needed. We're walking, talking monuments to the greatest extinction event in Earth's history. The Great Oxidation Event teaches us that life is resilient but not invulnerable, that change can be both catastrophic and creative, that today's waste can be tomorrow's resource. It shows us a planet in constant flux, where the rules of survival can change utterly and without warning. Most of all, it reminds us that we're part of a story billions of years in the making, inheritors of a legacy written in rust and oxygen, ice and stone.
Every breath we take connects us to that ancient catastrophe. Every green leaf, every flower, every bird singing in the trees exists because cyanobacteria once poisoned the world. It's a strange thought, isn't it, that life's greatest disaster was also its greatest opportunity. That a purple sky had to die for a blue one to be born, that 99% of all life had to perish so that the remaining 1% could evolve into the magnificent diversity we see today. The day Earth turned purple was the day everything changed. And in the end, perhaps that's what mass extinctions are. Not just endings, but transformations. Moments when life takes a desperate gamble and reshapes itself and its world entirely. The cyanobacteria took that gamble 2.4 billion years ago, and against all odds, life won. Different life, strange life, oxygen-breathing life, but life nonetheless. So here we are, children of catastrophe, breathing the waste product of ancient bacteria, living on a planet transformed by mass death into a world of unimaginable beauty and complexity. It's enough to make you see that purple sky not as a horror, but as a promise that even in the darkest moments, life finds a way to create something new, something wonderful, something worth taking a deep breath for.